Antimatter reacts to gravity in the same way as ordinary matter. Gravity acts the same on hydrogen and antihydrogen. Experiments conducted at CERN have shown that, like everything else that experiences gravity, antimatter falls down when dropped. Observation of this phenomenon has eluded physicists for decades. In a recent experiment, the alpha antihydrogen laser physics apparatus team at the European Centre for Nuclear Research CERN in Geneva obtained the first direct measurement of freely falling antimatter. Experimental results have shown that antimatter in the Earth's gravitational field behaves in the same way as ordinary matter. These findings did not surprise physicists, but they call into question some unorthodox theories that suggest gravity repels antimatter rather than attracts it. The experiments carried out show that, at least in the case of antimatter, anti-gravity does not exist. Measurements of the gravitational acceleration of antimatter have shown that it is close to the gravitational acceleration of ordinary matter, at 9.81 meters per second squared. Antimatter is certainly accelerating downwards, said Joel Fajans, a professor of physics at the University of California, Berkeley, who, together with theorist Jonathan Wertele, authored the experiment. The conclusion is that we will not be able to levitate using antimatter, he added. The result will not surprise physicists. Albert Einstein's general theory of relativity, although created before the discovery of antimatter in 1932, treats all matter identically, suggesting that antimatter and matter respond to gravitational forces in the same way. All normal matter, such as protons, neutrons, and electrons, has antiparticle counterparts, which have the opposite electric charge, and a few other quantum characteristics, and when they encounter the mirror images in normal matter, they annihilate. This experiment was the first time that the force of gravity on neutral antimatter was directly measured. This is the next step in the development of the field of neutral antimatter science, said Wertele, a professor of physics at the University of California, Berkeley. A different result would have serious implications, he added. Fajans noted that no physical theory actually predicts that gravity should repel antimatter. Some physicists claim that if this were the case, a perpetual motion machine could be created, which is theoretically impossible. Nevertheless, the idea that gravity could affect antimatter and matter differently was tempting because it could potentially explain some cosmic mysteries. If this were the case, it could lead, for example, to the spatial separation of matter and antimatter in the early universe, which would explain why we see only a small amount of antimatter in the cosmos around us. Most theories predict that equal amounts of matter and antimatter should have been created during the Big Bang, which gave birth to the universe. But observing this phenomenon has eluded physicists for decades. The real problem is that gravitational forces are incredibly weak compared to electric forces, said Fajans, adding that some experiments failed because direct measurement of gravity with a charged particle, e.g. a positron, is not possible because any scattered the electric field will deflect the particle much more than gravity. In fact, the force of gravity is the weakest of the four known fundamental forces, along with the weak force, the strong force, and the electromagnetic force. It dominates the universe because, at least theoretically, it influences all matter over huge distances. But for a tiny piece of antimatter, the effect is negligible. An electric field of 1 volt per meter exerts a force on the antiproton about 40 trillion times greater than the gravitational force exerted on the antiproton. A team of physicists from the Alpha project suggested a new approach. By 2010, significant amounts of antihydrogen atoms were being captured at CERN. So Wörtele proposed that since antihydrogen has a neutral charge, it would not be affected by electric fields, which should allow gravity to be measured. Further analyses of this concept prompted researchers to conduct a new experiment, Alpha G, in which the first measurements were made in the summer and autumn of 2022. The results, published in Nature, are based on simulations and statistical analysis of what the team observed last year. The results showed that the probability of gravity pushing antimatter away is so small as to be irrelevant.